Math is not always pretty. Here my objective is to find the area of the triangle created by these 3 points. In the past we've talked about how you can use a determinant, and that would be the most efficient way of doing this problem, is throw these points in a determinant to find the area of the triangle created by these 3 points. However, what I want to show you here is something called Heron's formula, affectionately known as Hero's formula. Now, this is going to take a little bit of time to develop, but the reason why I want to do it is I want to review some of the ideas we already have. For instance, in order to use Heron's formula, you need to find the distance between x and y, the distance between y and z, and then the distance between x and z. So in other words, I need the 3 lengths of the triangle. The beauty of these formulas that I'm showing you, when you're using the determinant, it doesn't require that the triangle is a right triangle. It doesn't require anything that other than that it forms a triangle. And so as I use Heron's formula, we have that same advantage. If you give me 3 sides to a triangle, then I can find the area of that triangle. In this drawn out example, I've given you 3 vertices. So now I have to find the distance of each of them. So I'm going to find the distance between x and y. And so my distance formula for x and y is to find the delta x and the delta y squaring each of those from those points. So for delta y, to go from 6 to 3, we drop down 3 units. To go from -3 to 1, we go up 4. Now as I apply this, delta x squared would be 16. Delta y squared, -3 squared, is 9. And the square root of 25 is 5. So I've got one length. I know one side of my triangle has a length of 5. Now, as I said, it's a little bit drawn out. I have to do this for each one of them. So now I want to find the distance between point y and point z. So once again, I have to do my deltas. To go from 3 to -2, I've dropped down 5 units. To go from 1 to 5, I've jumped up by 4 again. As I throw this in here, this would be 4 squared plus -5 squared. That's 16 plus 25, and that would be 41. Now, the square root of 41 doesn't break down nicely, so I'm just going to leave it as is, and we'll see that in our calculations. Next, I need to find the distance between z and x. So I'm going to do my deltas. To go from -2 to 6, that would be +8. To go from 5 to -3, that's -8. -8 squared plus 8 squared would be 64 plus 64. Now that would be rad 128. The rad 128 does break down into 8 rad 2, but I'm just going to let it be for now because I'm going to show how the calculator will use all these values to come up with the area of the triangle. The next thing that I have to introduce is the actual formula. The formula is done in a couple parts. First off, you need what is known as the semi-perimeter. Semi-perimeter is what it sounds like. You find the area around, or the distance around the triangle, and then you're just going to cut that in half. So I had lengths of 5, rad 41, and rad 128. So I would have to add these 3 lengths up and then divide by 2, and that is called the semi-perimeter. I'm going to give it a value called S. Now that's just the first part of the formula. So in my calculator, I can take, let me clear this out here, 5 plus the square root of 41 plus the square root of 128. That gives me this value here of 22.716 and so on and so forth. The important thing is that you don't cut off your decimals. If you're going to work with a decimal, you need all of those decimal values. So one way of working with this, I can just store this. You got a button right here, it's STO, it means to store. I'll store that value in, I'm going to call it alpha A. That means that anytime I call up alpha A, I now have that value. Okay, now I'll set my calculator aside for a moment. I'm going to write this number here, 22.7168 dot dot dot. It goes on. And then I want to finish the formula. Heron's formula, or Heron's formula, states that the area will be equal to, I'll brace it yourself, this formula gets a little bit long. It'll be the square root of S. Now S is the semi-perimeter that we just calculated a moment ago, where we added the 3 sides and then divided by 2. I forgot to divide by 2. Oops. Easy fix though. I'll take my alpha A, divide by 2. That should be 11.358, so on and so forth. I'll store that the same way that I did a moment ago. I just go store, and I can put it right back into alpha A. So again, I had to do the semi-perimeter. That's where I add the 3 lengths up, divide by 2. It's going to be 11 and change. Now Heron's formula says if you want to find the area, you simply take S times S minus whatever your first length is. So I'm going to call it L1 times S minus the second length times S minus the third length. As I said, it's not the prettiest thing in the world, but it's really not that bad after you do a few problems. So my area would equal the square root. Now I'm going to just go back to my calculator. In my calculator, I'm going to have the square root, and then I'm going to do each of these values. Recall that A was where I had my semi-perimeter. So I'm going to say alpha A times, now I do my parenthesis, alpha A minus the first length, which was just at number 5, times the semi-perimeter, alpha A, forgot to put a parenthesis there, alpha A minus the second length, which was square root 41, and then I'm going to multiply by alpha A minus a square root of 128. I close that out, and you see the structure here. I had the A times A minus the first length, A minus the second length, A minus the third length. Now I know I'm saying A, but A is just my semi-perimeter. So when I hit enter, I get a value of 4, which means that this entire area is 4 units squared.